chapter 10 focuses now on principles of cooking. So we've worked on and talked about everything leading up to cooking. Now it's time to talk about the principles of the cooking itself. So we need to understand a few things when it comes to heat. We need to understand what happens when heat is transferred and how it's done through conduction, convection, and radiation. We also need to understand what happens when you apply heat to proteins, sugar, starches, water, and fats, and what it does to those items when you apply that heat. So the first thing is what we call methods of heat transfer. And I'm going to ask you this on your test, and you need to know the three methods of heat transfer: conduction, convection, and radiation. So conduction means transfer of heat through direct contact of the heat. So best example is your saute pan. You put your saute pan on the stove and you turn on the heat. The heating source is in direct contact with the bottom of the pan, and through conduction, the pan gets hot. You then add the chicken breast into the pan. The bottom of the pan is in direct contact with the bottom of the chicken breast. Heat is transferred through conduction from the heat of the bottom of the pan into the chicken breast, and that's how the heat is transferred. Now you got to be careful because heat is continuing to be transferred, and if you don't flip the chicken breast over in this example, then you're going to burn the outside because of all the heat that's being transferred. Even though the heat is working its way in through the chicken breast, you need to make sure you turn it over so you get that more even heat distribution, and also to help make sure that it doesn't burn on the outside. So that is conduction. And so it's direct contact of heat to the item being heated. The next is convection. Convection is the natural movement of heat through air, water, or fat. And there's two different types. There's natural convection and mechanical convection. So natural convection is where the heating process does it all on its own without any other mechanical means. So your conventional oven is a great example of natural convection. There's a heat source at the bottom of the oven. So you turn the heat source on. The air that's at the bottom of the oven starts to heat up. Well, if you remember from science class, when something gets warm, it becomes lighter, and so it rises. So when it's rising to the top, the air that's at the top is cooler, it's heavier, it sinks to the bottom. It comes closer to that heat source, it warms up, and it starts getting lighter and going up. The stuff that's up at the top cools down, it becomes heavier, it works its way down. And so after a while, you get this natural circular motion of heat that's rising and falling inside your oven. Now put in a roast, and while that heat is circling naturally around in the oven, some of that heat is transferring into the roast itself. So in this case, it's that transfer of heat through the air. Another example of natural convection is boiling water. Again, same basic principle. You put water in a pot, you put turn the stove on, the water at the bottom starts to get hot. When the water in the bottom starts to get hot, it works its way up to the top. The heavier stuff comes down and it starts to heat up. Again, you get this circular motion of the warm water working its way up, the bottom, the cool water working its way down. You then have natural convection. You get it up to that point where it's moving so fast that it's creating those bubbles where you actually get the boiling or the simmering, depending on what level that you're at. Deep fat fryer works the exact same way as well. It's just with fat. So again, the fat is cold, it gets heated at the bottom, it works its way up, you get that same thing, it's just a thicker process. Now what's interesting is not all convection is created equal, because you'll find, and if you think about it, it makes sense, air is actually a very, very poor conductor of heat, where water and fat are better conductors. And the best way to think about it is, if you have a 350-degree oven and you open up the oven and you put your hands in to pull something out, you don't instantly burn your hands because the air is not conducting the heat well enough to actually burn you. On the flip side, if you have a thing of water boiling and you put your hand accidentally over the steam that's being created by that 212-degree water, it will instantly burn you because water is more efficient at transferring heat than air is. So, food for thought, if you are trying to cook something as fast as possible, you need to put it in a liquid or fat as opposed to cooking it via air. Now, mechanical convection says we take something outside of the natural circular motion and we help to move that product around faster. So a convection oven is mechanical convection. The fan forces the air around the food faster, which releases the heat faster, which speeds up the cooking process. Just the process of stirring a pan works the same way as well, because you are taking that stuff, like maybe it's a soup, and because it's heavy, it's not necessarily going to rise up on its own. If you leave it down there, it's going to scorch. So by stirring the pan or the pot that soup is in, you are using mechanical convection to move the warmer stuff up and let the cooler stuff work down below so it can be heated up by the heat source. So those are examples of natural and mechanical convection. Last but not least is radiation. And we're not talking about radiation that's going to grow you a third eye. We're talking about radiation that conducts heat. The first one is infrared radiation or infrared cooking. And that is where an item is putting off so much heat that the heat is being distributed as infrared heat. And the best way to describe that one is your grill. You get your grill started up and you're wanting to see if it's hot enough. What do? You put your hand, 6 inches, a foot or so above the grill, right? And you can feel that heat. The heat that you feel coming off of the grill, that heat that your hand feels, that's actually infrared radiation that's being released by the heat source. It's the reason why a broiler works as well. So you've got a heat source above, you've got something below it. It's not moving the air around it to heat it up. It's not in direct contact, but the heat source above on the broiler is getting so hot, it's releasing infrared radiation, which is then transferring that heat into that food product. Now, like with a grill, if you notice, a grill has grill marks, right? So the actual lines of the grill marks is heat transfer through conduction because that grill gets really hot. But then in between, they're not raw because you got the infrared heat that's coming up through and doing the cooking as well. But the combination of the conduction through the grill grates and being in direct contact with the grill grates, along with that infrared radiation, is what does the cooking. Plus, you get those really cool grill marks as well. So that's infrared radiation. Microwave radiation is through, well, what you'd guess, a microwave. When you turn the microwave on, it releases these microwave radiation. And what it does is it reacts with the water molecules that are in your food. So the water molecules start to vibrate. They're close enough together. They rub against each other. They create friction. Friction creates heat. That heat turns into steam. And so the food is cooked pretty much through a steam-based process because of the water that's being affected by the microwave radiation. And those are the 3 methods of heat transfer: conduction, convection, and radiation. And again, just as a quick reminder, on test number 1, I will ask you those 3 methods of heat transfer. You will need to know those. So, effects of heat. When we apply heat to different items, they end up doing different things. So when we apply heat to proteins, they do what's called coagulation. A starch will gelatinize, sugars will caramelize, water evaporates, and fat melts. So with protein coagulation, when you look at a raw piece of protein, like a piece of meat, it's probably the best example, you're going to find that it's very soft, it's very squishy. The proteins are loosely folded on each other. When you apply heat, what it does is those loosely folded proteins start to bind themselves together. They start to tighten themselves up. I akin it to like a spring or a slinky. So, when the spring of the slinky is all the way out, it's very loose, there's a lot of movement. As soon as you start compressing that spring or slinky, it starts to become firmer. And so when you apply heat to a protein, it's like compressing the spring or compressing the slinky. It's taking those proteins and it's starting to firm those up. Protein coagulation is the reason why experienced culinarians can tell how done a piece of meat is just by feeling it. When you're pushing on the chicken breast, you're pushing on the steak, what you're feeling for is the amount of coagulation of proteins that are in that piece of meat. And again, after time, you're able to associate a certain feel or certain firmness with a certain doneness. That's how that works. But protein coagulation is important because that's the reason why our products get cooked and they firm up like they do with anything that has protein in them. Gelatinization of starch. So when you take a starch like flour or cornstarch or any other style of starch, you add it to a liquid and then you apply heat to it. The starch begins to swell when it's heated. It starts to get bigger. And if you've got a certain level of starch to liquid, if there's more starch than liquid, it will eventually become a solid mass. So when you're working in baking, gelatinization of starch is important for crumb. So you're looking at the finish of a cake or the finish of bread. The only reason that stays in and it expands and it stays in itself is because of starch gelatinization. For us in 150, we're worried about starch gelatinization for sauce making, because when we add a starch to a liquid and then heat it up, the starch swells, thickens, and it helps to then create the thickness in the sauce. But then again, you have to make sure you're being careful with the ratio of starch to liquid. Too much, and you end up having spackle because it's way too thick. And so, but you can thin that out. You're looking to try to find that right consistency where it tightens up enough of the starch and binds it to the liquid to create that visual thickness that we associate with a starch. So that's where gelatinization of starch is important in the savory kitchen, is into our sauce making processes. Caramelization of sugar. It's really, really important for color. It's partially responsible for color and flavor in the crust of bread and the brownings of meat and vegetables. So if you've ever tried to, you saute a carrot, that carrot, when it's sauteed, will brown on the outside once it reaches a certain temperature. Right. However, if you boil a boiled carrot will never brown because the heat never gets high enough for it to start browning. And browning of sugars, you're looking in the low 300 range. Well, boiling is 212. So no matter how long you boil something, it's never going to brown because you're not going to get to that temperature. Now, you do have what's called the Maillard reaction, which is really important. Big parts is in candy making, but you also see it in meats. And what that is sugar breaks down in the presence of a protein. That does about 250. So when your steaks brown on you, you get that nice caramelization. It's not because they're full of sugar. It's because the tiny amount of sugar is working with the protein, and this Maillard reaction is occurring within the proteins and the carbs in order to brown at a temperature that's a little bit different than what you would have with a straight sugar caramelization. So for us, we got to think about, if we want color and browning on our product, we need to make sure if it's a non-protein that we get it above that 300 mark on the outside so the natural sugars can caramelize. If it's a protein, it's going to happen through the cooking process, through the Maillard reaction, assuming that we can get it up to that correct temperature. Water evaporation is really, really important because when you heat something, it's going to turn into steam, and steam is going to be released and vaporize. Our issue is there's so much water within our products, and we want to minimize the water loss, because if you lose too much water, then your product is going to be dry. So it's a matter of finding ways to minimize the water evaporation and hedge your bets to make sure that the stuff stays on the moisture end. Now, if you're using a wet or a moist heat cooking method where you're using liquid, it's typically, I don't want to say a non-issue, but the issue is minimal because there's water already there. There's already liquid on the outside, so you're not drying things out. But if you're going to throw something on the grill and do a dry heat method, then you have to understand that the more you cook it, the more moisture it's going to be lost. And if you lose too much moisture, you end up having shoe leather. So it's trying to hedge that bet and knowing that you are going to have moisture loss, water evaporation, but how can you regulate and minimize the amount so you still have a good finished product? Last but not least within is the fats melt. A heat will cause a fat to melt, soften, and even liquefy. We find that butter melts around 70 degrees. Body temperature, if you hold on to butter, will melt the butter. But fats do not evaporate like water. It doesn't turn to steam and evaporate out. The fats melt, and then we find what it does is it typically binds themselves to the proteins and the carbohydrates. And one of the things, like we talked about, I think it was chapter 7, fat equals flavor. The presence of fat helps to bring out more flavor because most flavor is fat soluble. So the fat and the flavor of the food bind themselves together, and then it gives you the appearance of more flavor within your food because you've added that fat. But we have to understand that that fat melts and that it can be absorbed into the food that we're working with, which if you have too much in, then it becomes greasy. So again, it's trying to regulate and maintain, okay, we're going to have fat melting into our product. How much is good and how much then is going to make something greasy? And so you've got to regulate that through how you do your cooking. How we determine doneness, talked a little bit about this with the protein coagulation. You can look at the physical changes of the food, the touch of it, how it feels. You can look at color and texture. Of course, the most accurate, and at the health department asks us how you test, is you test the temperature of the food during the cooking process. Use your thermometer, stick it into the center of it, and then find the temperature to make sure it meets whatever that minimum requirement is. Note that you will have, and we'll talk more about this in meats, poultry, and fish, you have what's called carryover cooking, knowing that once you take something off the heat, there is still some residual heat within that food, which means that it's going to still continue to cook even though you're outside of the cooking device. That's going to be really important in meats, poultry, and fish when we talk about roasts and stuff, because we have to take that into consideration when we are cooking to make sure we don't accidentally overcook something that we have in the oven. But even smaller pieces of meat, like steaks and stuff like that, still have some carryover cooking. If you don't put your carrots and and shock them in water, in ice water, you're going to have carryover cooking because there's still residual heat in that carrot that's going to continue the cooking process even though it's outside of the water. So carryover cooking is something we need to be aware of and making sure that it's being used as an advantage and not a detriment to the quality of our finished product. Finishing up then, we look at cooking methods. So there are 3 basic cooking methods. There's actually 2, dry heat cooking and moist heat cooking methods. The third one, combination, is not one on its own. It actually uses both dry and moist heat cooking. So there's 2 basic styles of cooking methods, and then there's a combination of the 2. Underneath dry heat cooking methods, you have dry heat cooking with air and dry heat cooking with fat. For moist heat cooking methods, you have moist heat cooking with water and moist heat cooking with steam. So for dry heat, the first ones, the broiling, grilling, roasting, baking, and barbecuing, are all dry heat with air, or dry heat with no fat. So broiling and grilling, the difference between the 2 is where the heat source is. Broiling, the heat source is above. Grilling, the heat source is below. A sidebar to grilling is griddling, Griddling. Same as grilling, but instead of having the grill grates, you have the solid griddle, like what we have downstairs in storage. And same basic principle, but you have that flat top or that griddle that you would cook on instead of the grill grates. Roasting and baking, the terms are exactly the same. There is no difference. However, typically roasting is associated with savory, baking is associated with sweet. Although it's not always that way. Like, for example, roast beef, again, we use roast. It would sound weird if we called it baked beef, right? But we call it baked ham. So it's kind of strange, but both of them mean the same thing, and you can typically use them interchangeably. A lot of it, again, is more of a menu marketing type of thing as far as what you're going to use as far as the name. Barbecuing is a variant of the roasting or baking. It's just at a lower temperature, usually for longer periods of time. Dry heat with fat are the three: sauteing or stir frying as a subset, pan frying, and deep frying. The difference between the three is how much fat you use. Sauteing, you're using a small, and stir frying, you're using a small amount of fat that you are cooking usually smaller pieces of product fairly quickly. Pan frying, you're using enough fat to cover the product halfway up, at least halfway up in the cooking. So like pan fried chicken, you want to make sure you have enough fat that goes and covers half of the chicken. You fry it on one side, then you flip it over and fry it on the other side. Deep frying, of course, means you are covering in the product all the way with fat. So that's the big difference between the three, is how much fat goes into it. And of course, you're going to use different products and different items for the three different things. What you would saute, you wouldn't necessarily pan fry or deep fry. There can be some interchanging between the pan frying and deep frying, but in a commercial kitchen, a lot, pan frying is probably one of the least done because it takes up a burner space that could be used for something else, where you can drop something in the deep fryer, totally submerge it, and you're cooking it all the way around instead of having to turn it halfway through the cooking process or what have you. But those are the dry heat cooking methods, either with air or with fat. Moist heat cooking methods are based on temperatures. Actually, I'm missing one here, I notice. Poaching, then there's simmering, boiling, and steaming. And all of those are based upon temperatures. That's where you're going to get the biggest difference between the three. In your book, in chapter 10, actually has your temperature areas. So poaching is typically around 165, sometimes 155, all the way up to about 180. The biggest thing with poaching is there cannot be bubbles, no bubbles whatsoever. If there are bubbles, it's too hot. The reason why, because when you poach, you usually poach stuff that are more delicate that would break apart if there are the bubbles there. So if you're doing a poached egg, if you get a big bubble from a simmer that goes through that egg, that it's going to rip that egg apart. Or if you're poaching a salmon and you've got, salmon when it cooks is kind of has a flakiness. Well, if you got a bunch of bubbles, those bubbles can actually flake the salmon while it's cooking. So that's why you do a poaching. The two is submersion or shallow. With submersion poaching, you're using a larger amount of liquid, and it's meant to just cook and go. So like you would submersion poach your eggs if you're doing a poached egg, because you're not holding it, you're not doing anything with the liquid or anything. With a shallow poach, you just do enough liquid to just cover the product you're going to poach. And then once it's poached, you usually pull it out, and then that liquid then a lot of times is turned into a sauce to accompany that product. So if you're going to do a poached salmon, you could poach a salmon fillet in some salmon stock and then take the poached salmon out and then add ingredients and turn that into a sauce that you would serve with that poached salmon. So it's being cooked in its own sauce that it's going to eventually be served with. Simmering is around 185 up to about 205. It's getting those small bubbles. Gentle bubbling is what you're looking for. Those are typically done with proteins if you're going to cook meat. Because the issue is, people say like boiled beef. You don't boil it, because if you boil it, it actually coagulates the proteins too fast and your product becomes tough. So you always want to simmer. Anytime you're doing a protein, if you're doing it in liquid, you always simmer it. Never, ever, 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 did I mention ever, boil your product. Boiling then is for your general vegetables and your pastas, your beans, legumes, things along those lines that are not affected by protein coagulation. All those can be boiled. And in fact, it's preferred because it's going to be faster than having to try to simmer them. Unless you're trying to do a dish that has meat in it and you're simmering the veggies and everything with it, then of course you want to do that simmering because of the meat that's in it. And sometimes, especially even if you're doing like a braised vegetable dish, sometimes people like to simmer it because it gives more time to release the flavors and allow the nuances to come through instead of a real quick type of thing. So sometimes you'll see, even like if you're doing a braised veggie or something like that, you would do it at a simmering temp instead of boiling. But boiling is typically, again, for those veggies, beans, legumes, starches, and pastas. Then the other side to it is steaming. So steaming, you're actually using the vapor that's being generated by the boiling to actually cook your product. So it's not in the water itself, it's usually above the water, or it's in a steamer that the water is next to it and creating steam and then going into the device, the piece of equipment that's being used. But that's, again, another very, very efficient way of cooking product and making sure that those things are being taken care of, is to make sure that you're steaming your product. But again, no direct water contact, just contact with the steam. Another fast way to cook veggies and stuff especially are very popular as far as steamed items. Now, combination, the first step in your combination cooking is you would brown the main ingredient using dry heat, and then you would simmer the liquid, the food in a liquid. So second step would be then the moist heat. So when you think about it, technically combination cooking is a moist heat cooking method, because the searing and with dry heat is really part of mise en place. It's part of your prep, right? So there are two types of combination cooking: braising and stewing. The difference between the two is the size of the product. So when you braise something, you're typically braising larger pieces of meat in most examples. With stewing, you're typically cooking smaller, like cubed pieces of meat. And then another big difference is how much liquid. So if you braise, you only need to bring the liquid up about a third of the way, maybe half the way up. You put a lid on it, and then the natural steam that's being created helps to cook the upper part, even though it's not totally submerged. However, if you're stewing, you usually have enough liquid to entirely cover the food and let that cook low and slow. And what that's doing is the moist heat cooking method is breaking down the connective tissue within the meat, which is what causes that meat to be tough. And if you break down that connective tissue, it helps to tenderize that finished product. We'll get more into that next 8 weeks in meats, poultry, and fish. Another modern take on combination cooking is through sous vide, where you're taking vacuum sealed pouches and you're submerging them in temperature controlled baths. So instead of just putting it in and letting it simmer, you actually control the temperature, and it's very, very precise. But you got to be careful that you're doing it right to make sure that it's still safe, because there are very specific time temperatures to make sure that we are pasteurizing our products during that cooking process, so it's safe for people to eat. The last thing you want to do is do a long cook through the sous vide, but you don't have your temperatures right, and then you make somebody sick, and especially through potentially botulism, because you're probably in an anaerobic environment with those vacuum sealed pouches. But there's a lot of possibilities. One of my favorites is 48-hour short ribs, where you take your short ribs, you sear them, you put them in the vacuum bags with your sauce and stuff, and then you cook it at 140 degrees in the immersion circulator for 2 days. So they are amazingly tender, but because they never went above 140, they eat like a medium rare steak. And so it's a really cool thing that you can only do through the immersion circulator and through sous vide that you couldn't do with a short rib in a traditional setting. Another one that I like doing, especially if I'm doing a large group, is I'll sous vide my steaks. So I'll put my steaks in the vacuum bags, and any mediums I'll put into water bath, around that 145-ish degrees. If you want a well done, I'll put it in at 155, 160, a different bath, and you let them cook for about an hour to 2 hours in there. And then all you got to do is cut the bag open, throw them on the grill to get some grill marks on them. Or if you're doing a banquet style, you can mark them first and then put the steaks in the sous vide. Then you just open them up and set them on the plate, and they're going to be perfectly cooked all the way through. They're going to be a medium all the way through, because again, the temperature never got above what would be considered the temperature for a medium steak. So they have some really cool things. Again, if this is something you're interested in, next time Chef Keith offers modern cuisine, take him up on that. You're going to learn all about that stuff. And that is chapter 10, ladies and gentlemen, all about methods of cooking. We are getting closer to actually starting cooking. Next week, we'll be actually putting these theories to practical use within the kitchen. Thanks for watching, and we'll see you soon.